MIRA. Three innovative solutions were implemented in the MIRA instrument: the dry point contact technology, the Ultramatrix multiple transducer focused antenna array, and the development of a digitally focused array software algorithm. The dry point contact ultrasonic transducers used in the MIRA instrument are constructed with a proprietary crystal tip and a high-performance composite damper housed in a very small casing. The actual contact surface area of the transducer's tip to the face of the test sample is so small that a coupling agent is no longer required. The use of multiple transmitting and receiving transducers electronically connected in a single array provided the much-needed ability to conduct one-sided tests. Experimental tests have shown a maximum depth of penetration of about 2 meters. The large area of the array provides a constant reception of the reflected waves. During the time of a double pass through the concrete structure, the ultrasonic wave partly scatters and gets absorbed, but the echo signal fixed not by one, but by 48 highly sensitive elements visibly stands out against the background of occasional re-reflections. The MIRA instrument can be used as a one-sided test method to investigate problems in high-rise building facades, tunnels and underpasses, highway pavements, bridge decks, etc. Having resolved the problem of dry point contact and the problem of a contact agent required for testing, we have got a synergistic effect. The design philosophy of the antenna array granted one more important advantage. Since every transducer is equipped with an independent spring suspension, the Ultramatrix array adapts to the relief of the object. You can work easily, even on coarse plates with roughness up to 1 centimeter. And the large area of the MIRA array allows the collection of data from the whole tested zone promptly. The MIRA instrument collects and processes data using a digitally focused array. The matrix antenna array of 48 elements literally stitches the object up at every measuring, transmitting 66 ultrasonic pulses into it. The elements of the array are controlled by a proprietary software that fires the incident waves in a sequential pattern. The sum of the total echoes or reflections is processed by the program almost instantaneously. A modified version of the well-known synthetic aperture focusing technique is used to construct in a few seconds, after the trigger button is pressed, a cross-sectional image of the area under the antenna array. The image is formed with more than 65,000 points by digitally focusing the ultrasonic pulse. The high resolution of the reconstructed images enables the MIRA system to locate flaws as small as 10 millimeters in size. By reconstructing the information from numerous transducers of the antenna array, a comprehensible image can be produced. Furthermore, a 3D image of the internal structure can be made with the help of the specialized software. The test results are shown as a typical B-scan, cross-sectional image of the area below the antenna along the plane parallel to the longitudinal axis of the antenna. The image can then be further post-processed and analyzed along any given plane using a personal computer. The image showing the internal characteristics of the test sample is visualized as a perspicuous color map. Every point in the zone of testing is depicted as a certain color scale, depending on the intensity of its reflection. Every reflector's position can be located with a high degree of accuracy. The tomogram shown was obtained from tests performed on fireproof plates of a glass melter. At a nominal depth of 130 millimeters from the surface, a cylindrical-shaped flaw, approximately 750 millimeters long, can be observed. The following tomogram shows a red zone corresponding to a voided steel duct in a concrete column. Displaying the test results as B-scan tomograms provides a simple way to understand the test results. But full appreciation for the MIRA equipment is evident when 3D models of the test results are generated.
The new MIRA system is, in my opinion, the most advanced ultrasonic system for inspecting concrete. First of all, it's an imaging system. You get an image of the interior of concrete practically in real time after you do measurements.
The axonometric image reconstruction makes it possible to readily discern internal flaws. It could be more evident only if the concrete would have been turned into glass. Numerous trials at independent scientific centers were an indispensable part of the MIRA development. One of these proving grounds was the Federal Institute for Materials Research and Testing in Berlin, Germany. A concrete block with embedded steel ducts was tested to determine the accuracy of the 3D image reconstruction software. The tests were performed by engineers and specialists experienced with ultrasonic testing and the MIRA system. A non-destructive testing engineer from Chicago, Mr. Aldo de la Haza, scanned the block's surface. He was followed by Dr. Herbert Wiggenhauser, an NDT specialist from Berlin. When all tomograms were collected, the MIRA system was connected to a laptop and the collected data was transferred. A proprietary software provided with the MIRA device processed the data, and the 3D reconstruction of the test specimen was displayed on the computer screen. The virtual model strictly corresponds to the geometry of the real object.
The second generation of the MIRA seems to be very promising technology that is going to allow us fairly quickly to produce images of the concrete structures and internal flaws.
Ultrasonic testing of a concrete wall panel was performed using the MIRA system to measure the thickness of the wall. At about 3 to 4 seconds after the system was triggered, the test results were displayed on the built-in screen. The bright red area in the tomogram corresponds to the signal reflected from the back wall. The thickness of the concrete wall panel is indicated by placing the cursor at the center line of the red spot and reading the corresponding depth on the metric scale on the left side of the tomogram.
This is a very, very promising system for a number of applications, starting from simple thickness measurements to measurements of, for example, tendon ducts. Even reinforcement can be inspected with that.
The third sample tested was a reinforced concrete slab with reinforcing bars placed at various depths. The results of the MIRA testing show the location of the first set of bars at about 50 millimeters. In this tomogram, the bright red area at about the 200 millimeter mark corresponds to a reflection from the bottom surface of the slab. Above this reflection, 3 additional red spots are shown. These spots are reflections from bars located directly under the antenna array. The metric scale on the left side of the tomogram shows the location of the reinforcing bars at a depth of 50 millimeters from the surface. The next tomogram shows the location of the next set of bars at about 30 millimeters from the top of the slab. Physical measurement taken at the edge of the concrete sample confirmed these findings. Since 2009, the ultrasonic shear-wave tomographic MIRA system has been purchased by private companies and research institutes worldwide.
Increased number of transducers has led to improved resolution of the images. The screen allows you to look at your results while you're testing.
People said it is a wonderful instrument, and compared to other methods, you can solve many other difficult applications.